In this video, we have to study the two notions of cells of the three-dimensional lattice and the Bravais lattices. If we take a face-centered cubic cell, we have two kinds of patterns, the patterns on the vertices and the patterns in the middle of faces. This cell is said multiple cell because its multiplicity is greater than 1, which is equal to 4, and we say that is quadruple cell. The same lattice may be described by the red cell, which is a rhomboidal cell, which is occupied only at the vertices, and we have the multiplicity which equals 1. So the rhomboidal cell is a primitive cell. Now we go to study the different type of face in a cell. In a cell like this, in a three-dimensional cell, we have three type of faces. The faces A, which is the front face and the rear face, the face at the behind. The B faces, which is the left face and the right face, and the C faces, which are the bottom face and the top face. We continue avec the three-dimensional cell type I, which is a body-centered cell. Here we have a pattern in the body of the cell. That is a multiple cell, and here it's a double cell because its multiplicity is equal to 2. We return to the face-centered multiple cell F, which is a quadruple cell, and which multiplicity is equal to 4. This is F cell. The A cell with face A occupied, it is a base A centered, and it is a double cell, multiplicity equals 2. In the same way, the base B centered is also double cell and multiplicity equals 2. And then in the same way, C, base C centered, has multiplicity also equals to 2, and we say that we have double cell. If we go now to the Bravais lattices in a two-dimensional lattice, we have 5 lattices. The first is the oblique lattice with A different from B and gamma any, but different from 90 degrees. The rectangular lattice with A different from B and gamma equals 90 degrees. The centered rectangular lattice, which is characterized by A different from B and gamma any different from 90 degrees. The square lattice, A equals B and gamma equals 90 degrees. And finally, the hexagonal lattice with A equals B and gamma equals 60 degrees. To recapitulate this information or these results in a table, we have the oblique lattice with this condition, rectangular lattice, another type of condition, centered rectangular lattice with this condition, and square lattice and hexagonal lattice. We have 1, 2, 3, 4 system, oblique, rectangular, square, hexagonal. And the Bravais lattice, we have the P Bravais lattice, the P and C Bravais lattice for system rectangular, and P for the square system, and P for the hexagonal lattice. We have 1, 2, 3, 4, 5 Bravais lattice for a two-dimensional lattice, which are distributed between 4-axis system. 1, 2, 3, 4. The axis system and the Bravais lattice 1, 2, 3, 4, 5. Now, if we go to the three-dimensional lattice, we have 14 Bravais lattices. We enumerate these 14 lattices. We have the triclinic system, and with this condition, we have one Bravais lattice, which is P, primitive. The monoclinic with this condition on the parameters, and we obtain two Bravais lattices. One found earlier, one here is found earlier, plus these two, we accumulate three Bravais lattices for a three-dimensional lattice. We continue avec the orthorhombic with this condition on the parameters, and we have here four Bravais lattices. P, C, I, and F. And we have 3 plus 4, we have until now 7 Bravais lattices from the 14. We continue avec the hexagonal. We have one Bravais lattices with this condition on the relation between parameters. And we find one Bravais lattice, hence 7 plus 1, we have now 8 Bravais lattices from the 14. For the rhomboidal, we have also one Bravais lattice, 9 until now. For the quadratic or tetragonal, we have two Bravais lattices, P and I, 9 plus 2, 11. For a cubic system, we have this condition, and we have three Bravais lattices, P, I, F. And we have totally 14 lattices or 14 Bravais lattices. Now we are going to show that this rhomboidal cell or the rhomboidal system is equivalent to an hexagonal system. We are going to project this cell on this plane P along this axis, or along this axis here, the principal diagonal. If we project this cell on the plane P, these two patterns are here. These three patterns in blue color are like this. These three brown patterns are like this. And if we continue, we have under the brown, we have one blue pattern, which is here. And under the blue, we have a red pattern. We have a red pattern here. And here, we are going to find over the blue, we find a brown pattern like this. And now we are going to draw this line here. The sequence here is the same like here. We draw another sequence here. We have the same sequence here or here or here. If we continue, we have this line here like this, and we have also another line here like this. And to terminate this draw, we are going to show this pattern here, which is red. And now we are going to join these patterns, these red patterns, and we find that this system can be described by an hexagonal system. Here we have an hexagon. And this cell is a multiple cell. It is formed by three equivalent cells. Here, 1, 2, and 3. We are going to color this cell here. This cell here. And now we are going to take this cell and to do the Cavalier perspective of this cell. Okay. We find the 4 pattern, the 4 red pattern here, and another 4 red pattern here, which here are in the position 0 and position 1. Position 0 we have 4, and position 1 we have 4. And we have 2 pattern, one at position 1/3 C, and the second and 2/3 of C, or the first at 1/3 of this blue diagonal, principal diagonal, and the second at the 2/3 of this diagonal. This type of cell is named cell type R. And here, as we have here 120 degrees, and here 90 degrees, 90 degrees, donc we have a hexagonal cell. But from this type of hexagonal cell is of type R.